we have been considering one of the central themes in linear algebra, namely the task of finding a basis with respect to which a given linear map has a simple matrix representation. Till now, we were interested in a diagonal matrix representation. However, we saw that this is not always possible. So what do? We look at slightly more general class of matrices. And one such class is upper triangular matrices. They are not as simple as a diagonal matrix, but they are still simple enough. Let us see what an upper triangular matrix is. A matrix is called upper triangular if all the entries below the diagonal is 0. More precisely, if A is a matrix with entries Aij, then A is upper triangular if and only if Aij is equal to 0 if I is strictly greater than j. We often represent an upper triangular matrix in the following way. If lambda 1, lambda 2, etc. up to lambda n are the diagonal entries, then we know that all the entries below the diagonal entries are 0. And we denote that by putting a big 0 below. And the entries above the diagonal are not 0, but we don't care too much about those entries. So we often represent them by a star. So this is how we denote it, and now let us look at an example. We will look at an example of a 3 cross 3 matrix. Let the diagonal entries be 1, 2 and 3. We know that the entries below the diagonal has to be 0. So we get a 0 here, a 0 here and a 0 here. The entries above the diagonal may be 0 or non-zero. To illustrate this, let us put 1, 0 and let the other entries be non-zero. So this is an example of an upper triangular matrix. We saw earlier that if the matrix of a linear operator with respect to a specific basis is diagonal, then all the elements of the basis are eigenvectors. Therefore, the span of every single vector in the basis is an invariant subspace. We will now see that something similar is true for upper triangular matrices as well. More precisely, we have the following theorem. Let V be a vector space and L from V to V an operator. The matrix of L with respect to a basis V1 to Vn is upper triangular if and only if the span of V1 to Vk is invariant under L. And this should hold for every k between 1 and n. Also notice that from now on, we will use the notation ut to stand for upper triangle. Let us now look at a proof of this theorem. We will start with this side of the implication. That means we will assume that the matrix of the linear transformation L with respect to the basis V1, V2, V3, etc. up to Vn is upper triangular. This implies that L of Vi belongs to the span of V1 to Vi, which means that all the elements L of V1, L of V2, etc. up to L of Vk is contained in span of V1 to Vk. Thus, L of span of V1 to Vk is a subset of span of V1 to Vk. In other words, span of V1 to Vk is invariant. And that completes this side of the implication. Let us now look at the other side of the implication. So we start with the assumption that span of V1 to Vk is invariant under L. This implies in particular that L of Vk belongs to the span of V1 to Vk, which implies that I can write L of Vk as a linear combination of these elements. So L of Vk is equal to A1k V1 plus etc. up to AKK Vk plus 0 times Vk plus 1 plus etc. up to 0 times Vn. Now notice that these coefficients form the kth column of the matrix. And we can see that the entries below the diagonal in the kth column are all 0. But as k was arbitrary, this implies that the matrix representation of L with respect to the basis V1, V2, etc. up to Vn is upper triangular. And this completes the proof of our theorem. Now we will use the second characterization to show that if V is a vector space over C, then given any linear operator on V, we can find a basis of V with respect to which the matrix of the linear operator is upper triangular. That is, we have the following theorem. Let V be a vector space over C and L from V to V an operator. Then there exists a basis BV of V such that the matrix of L with respect to the basis BV is upper triangular. Let us now look at a proof of this theorem. We will prove this theorem by using strong induction on the dimension of the vector space V. Notice that the result is obvious if dimension of V is equal to 1. So, as the induction hypothesis, you assume that the result is true if dimension of V is less than or equal to k. And we will prove the result if dimension of V is equal to k plus 1. Now, given a vector space of dimension k plus 1, to apply the induction hypothesis, we have to come up with a vector space of dimension strictly less than dimension V. How do we do this? We first notice that L has an eigenvalue. Let us call this eigenvalue lambda. Thus, L minus lambda I is not injective. But as the domain and codomain are both V, this would imply that L minus lambda I is not surjective either. But what does this mean? This implies that range of L minus lambda I is a strict subspace of V. In other words, if you define U is equal to range of L minus lambda I, then dimension of U is strictly less than dimension of V. Now, ideally, what do we want to do? We want to restrict L to U and apply the induction hypothesis on this restriction. But to do this, we have to show that U is an invariant subspace. Let us show this next. Now, to show U is invariant under L, we will take an arbitrary vector U in U and look at L of U. Notice that L of U is equal to L of u minus lambda times u plus lambda times u. But this is equal to L minus lambda times I acting on the vector u plus lambda times u. Further, notice that this belongs to range of L minus lambda I, which is equal to u. And this also belongs to u, as u belongs to u. Thus, the sum of these two elements belongs to u, or in other words, we see that u is invariant. Now what do? We look at L restricted to the vector subspace u. Now L restricted to u is a linear map from u to u. And u has dimension strictly less than k plus 1. Thus, by the induction hypothesis, there exists a basis u1, u2, u3, etc. up to um of u such that the matrix of L restricted to u with respect to the basis u1, u2, u3, etc. up to um is upper triangular. And we know that this is equivalent to the span of u1 to uj is invariant under the linear map L for all j. And finally, we will extend u1 to um to a basis u1 to comma v1 to vn of v. And we will prove that the matrix of L with respect to this basis will be upper triangle. Notice that L of vi is equal to L minus lambda I acting on vi plus lambda times vi. And this belongs to u, which is equal to span of u1 to um. And thus L of vi belongs to span of u1 to comma v1 to vi. If I is less than or equal to L, then this is a subset of span of u1 to comma v1 to vl. Thus, we see that L of span of u1 to comma v1 to vl is a subset of span of u1 to comma v1 to vl. The two expressions 1 and 2 together imply by the previous result that the matrix representation of L with respect to the basis u1 to comma v1 to vl is upper triangular. And that completes the proof of the result. We will now see some applications of this theorem. We will show that if a particular linear map has an upper triangular representation, then we can easily determine whether it's invertible, and similarly we can easily find its eigenvalues. Let us see these results next. Theorem: let V be a vector space and L from V to V an operator. If there exists a basis BV of V such that the matrix of L with respect to the basis BV is upper triangular, then L is invertible if and only if all diagonal entries are 0. Even though we state the theorem in this form, we will actually be proving the equivalent statement L is not invertible if and only if there exists a diagonal entry that is 0. Let us see how to prove this result. Before we start the proof, let BV be equal to V1, V2, V3, etc. up to Vn, and the matrix representation of L with respect to the basis V1, V2, V3, etc. up to Vn be equal to lambda 1, lambda 2, etc. up to lambda n in the diagonal, 0 below the diagonal, and above diagonal we don't really care too much. So let the matrix be as we have described. With this notation, we will now prove this statement. We will first prove this implication. That means we will assume L is not invertible. What does this imply? This implies that there exists some vector v in V such that L of V is equal to 0 and V is not equal to 0. There exists some such V. Now, because V1 to Vn is a basis, I can write V is equal to A1 V1 plus etc. up to An Vn. Now, some of these coefficients might be equal to 0. Let k be the largest integer less than or equal to n such that ak is not equal to 0. Then we can rewrite this as a1 v1 plus etc. up to ak vk, and we know that ak is not equal to 0. Thus, 0 is equal to L of V, which is equal to L of a1 v1 plus etc. up to ak vk, which is equal to a1 into L of v1 plus etc. up to ak into L of vk, which implies that L of vk is equal to minus a1 by ak into L of v1 plus etc. up to minus ak minus 1 by ak into L of vk minus 1. This implies that L of vk belongs to the span of L of v1, L of v2, etc. up to L of vk minus 1. But L of v1, L of v2, L of v3, etc. up to L of vk minus 1 all belong to the span of v1 to vk minus 1. Thus, this is contained inside span of v1 to vk minus 1. That is the coefficient of Vk when you express L of Vk as a summation Ai Vi is equal to 0. But this coefficient is equal to lambda k. Thus, lambda k is equal to 0. And this completes one side of the implication of the proof. We will now prove the other side. That means we will assume that one of the lambda k's is equal to 0 and show that L is not invertible. First, observe that if lambda 1 is equal to 0, then L of V1 is equal to 0, which implies that L is not invertible. So this case is really easy. So that's not the interesting case. So assume that lambda k is equal to 0 for some k that is strictly greater than 1 and less than or equal to n. This would imply that L of Vk will belong to span of V1 to Vk minus 1. which would imply that L of span of V1 to Vk is a subset of span of V1 to Vk minus 1. Therefore, we can consider the linear map S from span of V1 to Vk to span of V1 to Vk minus 1 such that S of V is equal to L of V. But notice, as this list is linearly independent, the domain has dimension k, and similarly the codomain has dimension k minus 1. Therefore, S cannot be injective. In other words, there exists a vector V such that S of V is equal to 0. But V is not equal to 0. But S of V was defined to be equal to L of V. Thus, there exists a vector V such that L of V is 0 and V is not equal to 0. Thus, L cannot be invertible. And we have completed our proof. The previous result helps us understand the eigenvalues of a linear operator that has an upper triangular matrix representation. More precisely, let V be a vector space and L an operator on V. If there exists a basis V1 to Vn of V such that the matrix representation of L with respect to the basis V1 to Vn is upper triangular, then the eigenvalues of L consist precisely of the diagonal entries of the matrix representation of L with respect to the basis V1 to Vn. Let us see a proof of this theorem. Let the matrix of L with respect to the basis V1 to Vn be equal to the matrix that has its diagonal entries equal to lambda 1, lambda 2, lambda 3, etc. up to lambda n. All the entries below the diagonal are 0 and we don't really care too much about the entries above the diagonal. If this is the case, then the matrix of the linear transformation L minus lambda I with respect to the basis V1, V2, V3, etc. up to Vn would be equal to the matrix that has its diagonal entries equal to lambda 1 minus lambda, lambda 2 minus lambda, so on up to lambda n minus lambda, and the entries below the diagonal are all 0 and we don't care too much about the entries above the diagonal. Now notice that the previous theorem told that this linear transformation is invertible if and only if none of the diagonal entries are equal to 0. In other words, this is not invertible if and only if one of these diagonal entries are equal to 0. That is, lambda is equal to one of the numbers lambda 1, lambda 2, lambda 3, etc. up to lambda n. In other words, lambda is an eigenvalue of L if and only if lambda is equal to lambda I for some I. And this completes the proof of our theorem.